I work exclusively with corals and speleothems, and I work exclusively in the tropical Pacific. So I have a very kind of El Nino-centric view of all of these issues, approaching it exclusively from a reconstruction standpoint, so reconstructing tropical Pacific climate change. So what I'm going to present today, hopefully, is some frameworks for how we can understand how ENSO may behave in a greenhouse world, and using some specific paleo examples in combination with some modeling, some paleo modeling, and some GCM modeling to kind of think about if there's something we can learn very concretely with a lot of uncertainty, if that makes any sense, from this approach. Oh. Anyway, as I said, I'm approaching this from a ENSO-centric viewpoint. So ENSO means, yes, good. ENSO is short for El Nino Southern Oscillation, as I'm sure most of you know. And George gave me the title, or somebody gave me the title, which was not my usual song and dance. So you bear with me while I try to address what I hope is a relevant issue for the discussion here with regard to the paleo and modeling look at this particular radiative forcing on ENSO. So here I've modified this because this is basically me trying to piggyback on the immense popularity, and I'm such a big cheerleader for that movie, and I thought it was great. So my whole stance, the whole talk, will start with a discussion of basically a threshold that may exist in the tropical Pacific regarding changes in the property of El Nino, whether it's intensity or frequency, in a greenhouse world. So I've been working on corals. Yeah, if you want to, that'd be great. Okay, so these are some results from, this is probably the most well-known example of a simulation, a GCM simulation, forced with future CO2, looking at how El Nino will evolve in a greenhouse world. And this certainly got the most press and woke a lot of people up to this issue. And since then, there's been a lot of other work, which we'll talk about in a second, questioning this, talking about the complexity. But this remains a serious possibility and something that it's a good starting place. So this is a paper by Axel Timmerman, who I think was going to be here.
He's going to come tomorrow at 11.
Great.
The red eye.
Okay, so he doesn't get to see me make a mess of his work. So in this run, basically, they took a GCM and they forced it with in the greenhouse world, basically. And this is the response that they got in the tropical Pacific. So this is down to 200 meters across the basin. And what you see is basically a surface warming. And for our purposes, what we need to take away from this is that it's larger in the east than in the west. This is, of course, maps onto, in a very, very coarse sense, an El Nino event itself. Hence the idea that we may move into an El Nino-like scenario in a greenhouse world. Okay. Now you can also look at, because this was an ENSO resolving model, so they actually saw El Nino events, they're not just doing a radiative balance kind of approach. And you can look at what El Nino did in that same run. And you see this on the bottom here, and I'm sorry the green didn't come out. But there are three curves on here. There's a control run that they did with not the radiative forcing from CO2. And you can see that in green going along. There's variability in this system, a lot of variability in this system. There's the red, which is the evolution of El Nino intensities and standard deviations over the last century. And then there's the black, which is the CO2 forced run. And this is a running standard deviation. So this peak right here at the end, at about 100 years out or so, is showing you that there's a large step. I don't know, I haven't seen the raw data, but this reflects a significant increase in the amount of El Nino variance towards the latter portion of this run. So that's what was published, and that's what basically made a large amount of controversy and people running after this in a lot of other models, and we'll go to those results in a second. But I'm not going to get into why this was for this group, but it has to do with the cloud feedbacks, how the clouds are handled in the west versus how the clouds are handled in the east with regards to radiative balance. But we won't get into that, and I'm not an expert, so it's even better.
Is the top right average or instantaneous?
Is what?
The top right picture in the previous one.
I think that's average over the last portion of the run. This one, I think this is a kind of a 95%, you get yourself beyond something that is in the control run probably, but I'm not exactly sure what the blue line is.
So 5% of the values are above the 95%.
That may be so, Carl. There is a response here, and if you look at the raw data,
It looks to me like the upper bound of the control run, because the green just touches, kisses the middle line.
Anyway, unfortunately, I don't know what the blue line is, but let's just say it ignited a controversy. I'm not going to stand by these results, and nobody really would, because next. Okay, let's go through this slide, because basically the bottom line is to give away my very next slide. People who have pursued that kind of a run in many other types of GCMs. I think 20 atmospheric GCMs forced with CO2 have determined that basically there is no statistically significant response in the El Nino system to greenhouse warming. So that's what they found. That's where we sit. Some of them show La Nina-like response. Some of them show El Nino-like response, but the vast majority do not change in terms of those properties over the course of the run. So that's where we stand with what GCMs can give us for forecasting power. Okay, that's where it is. The rest of the whole talk is going to be about what we can understand from the paleo record, because there are some really unique examples about how ENSO may or may not have responded to radiative forcing, including heating. Okay? So here is a framework that I thought I'd discuss, because it kind of it's one of the real only frameworks for paleo people to grab onto in terms of how radiative forcing may affect El Nino. And this comes out of Mark Keynes and Amy Clement's work. And I kind of feel like Amy Clement, because a lot of this talk is basically pulling off of her various modeling results. But let's move through this. This is called the ocean thermostat. So here you have the tropical Pacific. This is from a paper by Mark Kane, showing a La Nina-like response, in this case, using his ENSO model, forced by CO2. Okay, this is going to colder temperatures, kind of an intensification of the cold tongue, increased upwelling in the eastern Pacific in response to greenhouse forcing of his model. That's just neither here nor there. It's not a GCM. It's not meant to tell us anything really accurate about the future, but it's illustrating a response in this El Nino model to radiative forcing. It's possibly could come true. This is the one thing that didn't come out, this slide in the Mac version, but I wanted to walk through this because it's important, because it is one of the still reigning paradigms for understanding how uniform heating at the tropical Pacific may affect the El Nino system. So if you don't get this, please ask me, because it's very important. So here was supposed to be the cold tongue and the warm pool. So it's hidden under this uniform heating block that I put on there, which is kind of overriding everything else. So you have, of course, mean winds pushing from the cold tongue to the warm pool, and that's kind of the annual mean state of the tropical Pacific. Now, if you impose, as they did to get this model result, you impose a uniform heating just by heat flux, basically. You just heat this whole box uniformly, which may or may not represent what's going to happen during a global warming scenario, but that was their clear implication of doing this. Uh-oh. Great. So what happens is that basically, because you have upwelling of cool waters from depth in the east and no upwelling here, kind of a stagnant ocean with just a deep mixed layer, then you have a buffering of the heating here. Okay, it wants to heat the water, but because there's a presence of continuing input of cold water, it does not heat very much, does not heat very efficiently. Versus in the West Pacific, you do heat very efficiently. There's no cold water being brought up from below to kind of mix with to abate the warming that's coming from the atmosphere. Okay, so what does this get you? This gets you warmer here, and let's just say not as warm here. That's their only point in saying this. They're not trying to say how much, what the difference is going to be. They're simply saying less and more warming as a function of uniform heating. So what does this do? This speeds up a feedback which exists in the tropical Pacific between the atmosphere and ocean, where you augment the winds. Okay, you're increasing the contrasts from east to west. The winds are going to respond. Upwelling intensifies as a result of this feedback. And of course, you push yourself into a La Nina type situation, increasing even more that gradient. And that's how they get this result out of that model. That's the physics behind that result. Well, physics, the arm waving or whatever you want to call it, the back of the envelope kind of thought. It's called the ocean thermostat. And this is one of the most, this is really the way that they've been able to address a variety of problems by simply taking their ENSO model, which basically covers more or less this domain, and they force it with a variety of radiative forcing, including some things that are really relevant for paleo timescales. Here's that promised result from the 20 GCM runs forced by greenhouse warming. And basically, here's the histogram of ENSO-ness of response. That's a new term, ENSO-ness. So on the left here would be a La Nina-like response in the model. On the right would be El Nino-like response. And you can see, of course, basically.
Essentially, that the gradient, the east-west gradient is getting stronger or weaker?
Right.
Okay.
Right. Yeah. How much that the mean response maps onto an ENSO-like pattern is what my understanding it is. Okay, so you can see here, big fat zero in the middle with a couple kind of equally distributed on either side. So that's where we stand for a forecast of this as best we can do. Okay, go ahead. So I'm going to now turn to the paleo record, and I'm going to look at 3 different timescales. One, basically, 2 of these are a little bit more relevant. But this one has been looked at much more extensively and easier to look at because it's a low frequency kind of time scale. So this kind of goes from Milankovitch forcing, which we won't get into, but this is kind of what we think paces the ice ages. This is the coming and going of ice ages. This is the abrupt climate change that occurred during the last glacial and on the last deglacial that Klaus Keller just showed the Younger Dryas. That was the abrupt climate change event from the glacial to present, and my own specialty, the last millennium. And here's my research site, which I always throw on there to just, just give a breath of fresh air to everybody. And these are the fossil corals that I work with for my thesis and I'm continuing to work on now. So, and they play a strong role in kind of thinking about the last millennium response event. So let's go on. All right, so here we have the orbital forcing scenario. Again, this is using the Kane-Zibiak model, which is simple enough that you can run it for a long time. That's why it stands as the kind of, benchmark for paleo people to look at, because they have done these long runs and ensembles and they have done a lot of work on orbital timescales. So this is Amy Clement's work. And what you can see here is that this is forced by some radiative changes that occur over the ice ages. Okay, every 20,000 years, basically. This is radiative forcing called processional forcing. And here you can see the modeling run on the bottom here. So this is 140,000 years ago to present. We say 140, but it's 140,000 years to present. And here you can see that basically what they're seeing in their model, let's go to the time average response of the ENSO in their model. You can see on the bottom panel. So they're forcing with radiative forcing, which I'm not showing. It peaks and dips every 20,000 years. And you can see the time average Nino 3, which is the prime index of El Nino activity in the tropical Pacific, goes up to warm, down to cold, warm, cold, warm, cold. And it's basically tracking that forcing very, very well. It's responding to that radiative forcing in their model. Now, I think it's always more illustrative because this is shown all the time without this. So this is what the warm period looks like. This is the warm El Nino that they get on the top, and this is the cold El Nino that they get. The differences between these peaks and dips are actually, you can see it right up here. And what you can see is that if you time average this, you're going to get more activity, more El Ninos up here. Here you get fewer El Ninos. So here you end up with more regular, higher El Ninos, and here you get less frequent, irregular El Ninos. So the oscillation between the Pacific being in this kind of state to this kind of state causes these 20,000 year cycles. Now this should be testable in paleo data. Okay, so we can go look at that now. And that's actually harder than it sounds, unfortunately. We have some new records coming out from spielethems that are going to be exciting, hopefully, but so far it has been more difficult than we would like to test this theory. So this is work from a colleague of mine, Sandy Tudhope, using fossil corals that grew over the last glacial cycle. So what he's asking, if you can go back one maybe, what he's asking is if we get corals from this warm period and this cold period, are they going to show us this El Nino versus this El Nino? That would be good. That would be strong confirmation potentially of the Clement results. So now you go forward, we can look at this. So here's the last glacial cycle. Time has been flipped now back to the paleo way of doing time. So this is present, and this is the last interglacial, the peak interglacial conditions. And here's his coral ENSO strength from the corals that he has. Of course, they fall at different time slices going back. And what you can kind of see, here's Amy's results down here with the Niño 3 going up and down every 20,000 years. What you basically see and what they have to say in their paper is that there's no primary control of ENSO in these corals from this kind of a framework.
Could you explain the diagram again?
Yeah, so this is going back in time. So here's present going back. Here's sea level and West-East Pacific, West Equatorial Pacific SST. So these are measures of a mean state in a glacial interglacial sense. This is interglacial conditions, glacial conditions, and then the last interglacial stage.
Is it a model result or is it?
These are both paleo data reconstructions at very low resolution that have been around for a long time, sea level and Western Equatorial Pacific. This is the modeling result over the same period going back in time. And this is the fossil coral results. So these are only windows of this long. We're talking 60 years, 10 to 60 year chunks of visibility onto how El Nino behaved at these particular, you can't see the gray bands, but there are gray bands running through here at various time intervals. So you can test the Clement kind of model.
In the lower record, and maybe it was on one of the earlier slides, that a 20,000 year periodicity is not obvious to me. There's a lot of other stuff going on there.
Yeah, there is.
So if you run the model without any 20,000 year variability, what does the curve look like?
They didn't show that, but I think not in this kind of a sense anyway, not in this time average sense, but the Kane-Zebak model just has a kind of a regular El Nino that dances around.
I don't think that would be the obvious description of that record, that it is dominated by 20,000 years.
Well, there's actually an 11,000 year thing in there that's beating too a little bit. We'll get to that. We'll get to that. It's relevant to the discussion. But for now, at any rate, what you can see, what comes out of this work where you have these little glimpses into El Nino is that it does not map very well on this 20,000 year framework that Clement et al. Put forward to explain El Nino. Yeah?
One of the most interesting predictions to me of that work was that ENSO should be more powerful in glacial maximum than under present circumstances. Is that the correct interpretation of the fourth the lower set of data from the Kane-Zebak model? Yes.
Yeah, well, I think that depends what you call the glacial, of course.
At LGM.
LGM, right.
LGM.
So here, I guess, where's the LGM? Yeah, I cut the time axis off, but it's right here. It's right here. So there's a peak here, a weak peak.
At that point at all, I see it to the left of that.
This one.
Yes.
You start coming out of the glacial.
That looks like LGM to me.
Yeah, they don't have a framework for how to interpret how the LGM might affect these results, and we'll come back to that.
But in the Todd Hope et al. Data, there's basically no data from that time slice.
Yeah, this is what the closest they come to glacial, which is not appreciably lower or higher than anything else. So it's
can't really say anything.
You really can't say anything as the bottom line. I don't want to take it much further than that, but if this was a very strong control, you might have expected this to map much more reliably onto this 20,000 year framework, and it doesn't. So they give a variety of arm waving things to explain that, but we're not going to go into that. Okay, so this was hopeful, but kind of not so tightly correlated. So go on.
Hopeful.
Well, in the sense that corals, it's a beautiful coral record. It took a lot of effort, and so kudos to that. Maybe one day, if we had enough records, perhaps we could address this in a more statistically significant framework. Then look at 10 years at 38K and call that, representative of a 10,000 year piece of climate. So
They didn't get conclusion to draw from your diagram.
the conclusion is that they'd hope to test the Clement et al. Work with those fossil corals, and what they showed was that that does not exert a primary control on El Nino as far as those corals say. That's
Of Dick's question, this was just the Kane-Zebak model, so changes extratropical.
All bets are off.
So what is the LGM in that model mean?
We'll come back to that. Actually, it's a great question.
This is the 747 versus the PC.
Yeah. This is my last slide. So if you just let me get there. Okay. So this is another example. I'm not going to go into this record too much either, of course. But this is a record of magnesium-calcium base sea surface temperature in the eastern equatorial Pacific cold tongue. Okay, cold tongue SST. We're looking at relative changes from LGM to present in a very low resolution noisy record. That's what you see here in these purple dots. And you can see the record here, and they also hoped to see, or we're trying to see, hoping to test the Clement et al. Framework, which this is precession coming along right here, equatorial seasonality, which kind of increases or decreases the seasonal response on the equator here. And what you can see is that, I mean, there's some suggestion that there's a dip in the mid-Holocene here. So this is at 6K, 6,000 years ago. There's some suggestion that, of course, well, now you get into the last glacial. So this is cooling that could be attributed to a lot of other things. But this kind of shape here that they found what was maybe indicative that on a very long time scale, if we had records from the tropical Pacific, which we don't have very good records from the tropical Pacific, you would be able to see something like this. That's what they found from this exercise, which again is not very refreshing, not very sink your teeth into type stuff. Okay, so here's where we move to the abrupt climate change example. So this is taking the same model, of course, running it for these paleo timescales, which is very useful. And this is a very well-reproduced figure from Clement's 2001 paper where they address abrupt climate change and the potential for the Kane-Zibiak model, this is only the Kane-Zibiak model, to basically get locked into a phase for regime for hundreds of years potentially, where it actually does not exhibit its normal El Nino behavior. It actually gets locked to the seasonal cycle, which is in this model. It's forced. Okay, so they have a locking to the seasonal cycle, which is this phase right here. So what's happening is that it's forced by precession. It's forced by processional forcing. So there's a big curve of processional forcing coming through here from last glacial up into 10,000 years ago, a 10,000 year smooth curve of forcing. And what they see here is between their cold phase and their warm phase, they see this kind of behavior in their model. They don't see it all the time, but they see it frequently, what they call El Nino breaks. So can you get stuck is the question that comes out of this type of study. Can you get stuck in the El Nino sense to a different regime, be it a seasonally locked regime or any kind of other high intensity regime? And then you can affect global climate patterns that way very easily, obviously, if you just wipe out El Nino all of a sudden. Okay, so let's move on and we can look at what the paleo record can bring to bear on this. And it doesn't exactly comment on the Kane-Zibiak results, which are kind of highly idealized. But it does, this graph is only intended to show you that we recently have some records that confirm that the tropical Pacific, I'm not saying El Nino per se, but the tropical Pacific has played a role in abrupt climate changes, probably all of them, of the past. So that's one of the other take-home messages from this talk. So here you have the GISP ice core up here, the poster child for abrupt climate changes with all of its wiggles going up and down, present to 70,000 years ago. And here's stage 3 variability, the abrupt climate changes of stage 3 and the Younger Dryas. Here are two different records from the same sediment core in the western equatorial Pacific. You can read this as salinity in the western equatorial Pacific. Salinity in the western equatorial Pacific is highly driven by El Nino type changes, among other things, but it is one of the primary regions where rainfall affects, rainfall associated El Nino, ENSO associated rainfall occurs in the West Pacific. Severe drought every time El Nino event happens there. And this is also noisy, lower resolution record than you'd like, but you can kind of see that every peak up in the Greenland record, every warm abrupt climate change event is mirrored by a decrease in this parameter here. Basically, these are inverted axes. Okay, so this would mean fresher conditions. This is a variety of age controls, including magnetic events in the sediment core and radiocarbon dates. Only through here, so yeah, only through here. And then they have a couple magnetic features down there, and then it's wiggle matched. So they assume that what happens here in the portion that they can see maps in phase space out to the rest of it. So yeah, okay. Past 50K, it's assumed. They have the Lechamp event, some radiocarbon aids, and then beyond that. So yeah. But nonetheless, I am convinced, mostly by things like this, the Younger Dryas, and some of these larger events, that there is an impact in the tropical Pacific of these type of events. This is not the only line of evidence for this. We can look at another one in 1 second. So let's go to the next slide. This is another much higher resolution record from the South China Sea. This is basically temperature going up here in the red curve. This is that previous record from the Eastern Equatorial Pacific, which shows you not a very large Younger Dryas signal here at all. Okay, nobody can argue that in that record. And then this reversal here that is associated with the Younger Dryas. Now this is radiocarbon dated quite extensively. So there's not much wiggle room here for talking about this. So they see this reversal that coincides with the Younger Dryas, the Greenland Northern Hemisphere Younger Dryas event. And then, of course, a Holocene record after that. Okay, so it does seem to participate. The tropical Pacific does seem to participate in the abrupt climate change events. And I think that's the take-home of these slides. And the framework for understanding that could be an El Niño response to smooth radiative forcing. That's another take-home from the Clement model. We can't test that right now. We don't have the records to test that, but that is one way to put those two together.
You always show here one curve, and of course the question of uncertainty comes too. But what about the uncertainty of these strong gradients? How sure are we about the fact that they're so strong is depicted in this diagram? Since the numbers are uncertain, and also the derivatives to some extent.
You mean like changes like this?
Well, the red curve, which is falling down there first.
Right.
I'm not sure. Right. How sure are we about that? I mean, what's
that
the
curve?
expected error of
the
derivatives? Do we know the expected error of the curve itself?
No, not really.
Oops.
No.
That's not good, is it?
No, that's not good, and I wish that we would get more money to reproduce more cores, but we don't.
The statement you just made implicitly assumed that the uncertainty is zero, right?
Yes, I did. That's basically I'm telling you a story. It could be completely wrong, but these records are so new and they're so unique at this point that we cannot, bang on a table and say that this is the way it was. But it is definitely suggestive. I would go a little bit beyond suggestive, and that's where I'll leave it. Yeah.
But it seems to me that the fundamental issue which is raised by these intercomparisons is the question as to whether the connection between these cold events and what happens in the tropical Pacific has anything to do with the direct impact of radiative forcing, or whether it's just a reverse teleconnection from the high latitudes to the low latitudes.
Yeah.
And I'll argue very strongly that it's the latter effect which is actually operative.
Yeah, many people would argue that. I will say, until proven wrong, which will take a lot of records, that we've not ruled out the possibility that the tropical Pacific acts as a trigger for any of these events, and that's a controversial statement. But I believe it cannot be ruled out at this point. That's all I'll say. And I find it very exciting that, in the big universe, you step back a bit. I find it very exciting that we're finding evidence of abrupt climate change events in the tropical Pacific, because I feel that it has been missing from the discussion. Whether you talk about it as a trigger or a feedback mechanism, it should be in the discussion. Yeah. Okay, so let's move on. Okay, so now we're going to move to the last millennium, which is much, much closer to home, and my last kind of mini example here. And we're going to go through some effects of radiative forcing that are not involving slow changes in precession and glacial to glacial timescales. Now, of course, we're talking about volcanic and solar forcing, which is in some ways more relevant to today. Certainly the boundary conditions are more relevant to today. So this is a study where they took volcanic eruptions that have happened over the last 400 years, the largest eruptions that have happened in the last 400 years, and they looked at how the El Nino system responds to those. So they took if it responds to those. So they composited 10 years with the eruption in the middle. They took 10 years around each of these very, very large eruptions, and they stuck them all together and averaged the response. What you can see is that on average, here's year 0 during the eruption. On average, after the eruption, there's a slight tendency towards El Nino type response with a following La Nina, of course, which is very common. Once you have an El Nino event, you go into La Nina. So they see this response here, which is not highly statistically significant, but they have some variety of parameters, ways of gauging its statistical significance, and they say that it is 99% significant, this kind of response. Okay?
So the imposing volcanic eruptions, again, as a change in the radiation.
This is actually proxy data. I'm sorry, I should have been very clear about that. This is a proxy-based study, has nothing to do with modeling. They're actually taking volcanic eruptions from known eruptions from ice cores and looking at the response in the tropical Pacific based on our best reconstructions of the tropical Pacific, which is also, that's why this gets into a lot of error very quickly. But a very interesting, this idea has been around for a long time. This is kind of the first statistically rigorous whack at it. This is basically comes out of Mike Mann's lab.
What are the 3 different plots?
This is a variety of using different kinds of eruption. Yeah, so different records of eruptions. They don't agree perfectly, unfortunately. So this is a VEI, an IVI, and a VEI. This is 10 of the strongest events, 13 of the strongest events, and then this is basically, as you can see, over different time periods. This is, 200 years to 1889, 1979. So they're just trying to give you a flavor that they have tried a lot of different kinds of combinations.
So on the left-hand one, I could infer that El Ninos trigger volcanic eruptions 5 years later. Is that the proper interpretation?
No, the proper interpretation would be that
The blue here.
this blue here.
Yeah, the blue is everything occurring 5 years before.
Well, the other ones definitely don't bear that kind of interpretation out. So you would be
right?
okay. This launched a whole line of work that is very, very, very hot right now, and it involves the possibility that El Nino responded to radiative forcing over the last millennium. Now, I hadn't heard of that until about 6 months ago, and I'm going to present some results that have been done with the Kane-Zibiak model. This gets really boring, but I encourage all of you to go out and to make another ENSO model. So let's go on. Let's just look at that. So what they did, this is a model now. So this is no proxy data right now, simply looking at forcing the Kane-Zibiak model with the solar and volcanic radiative forcing of the last millennium, and what happens in that model. Okay. So here you have the volcanic forcing in blue over the last millennium, and the response, the Kane-Zibiak ensemble mean response to volcanic forcing, the Nino 3 index of that model. And you can see that even in the model, they have a response that is El Nino-like to large eruptions. Okay, that does go in line with the proxy-only study I just showed you in the same sense. Okay, that's what they saw in their model. And here you can see the solar forcing down here, solar forcing in blue, the ensemble mean response of the model in red. And what you can see is an inverse relationship where you have increased solar radiance and you have a decrease in the Nino 3 index, effective decrease in a mean sense. Okay, so that's a kind of an inverse response. Now, this is all should be echoing in your head, this ocean thermostat mechanism that we talked about with the Clement et al. Kind of framework, where if you heat the tropical Pacific, you end up in La Nina, and it kind of stands to reason by the reverse logic, if you cool the tropical Pacific, you end up in El Nino. And that's the mechanism they invoke to explain this behavior. This is what they see. So let's go to the next slide. Let's throw in some proxy data, in this case, my proxy data. This is corals that grew during the last millennium. So corals, basically, you can read this as temperature, more or less. Coral high is warm, and low on this plot is cool. And these fall in different intervals of the last millennium. Unfortunately, not as many as I'd like, but this is very laborious stuff. Here's the Niño 3 response in the Kane-Zieback model, solar and volcanic forcing combined. It's all they're doing in that model. And they argue, and I don't know what I would say. I'd say it's interesting that it does this well, that the coral mean, which is in blue, kind of falls close to the Kane-Zieback model mean, which is in red, within the ensemble errors, which are very large, and within my coral errors, which they don't plot, which are also very large. So let's go to the next plot. I'll show you the update of this. So here's the new Palmyra coral data that they didn't have when they published this paper. Not looking, yeah, your chuckling is not looking so good anymore. And here's my errors, actually, that I have my best guess errors on my ability to reconstruct mean climate, reconstruct Niño 3. So what you can see is you have these really cool conditions back in the early part of the millennium, and then you have kind of these conditions these are very large El Nino events here, these more kind of average-like conditions. But this is now the big, according to the work I've just done, we're throwing a lot of work into this, trying to figure out what is going on here. Are the corals crazy? Is this be some response to this radiative forcing that we don't know about? But the Kane-Zieback model no longer seems, if the corals are correct, the Kane-Zieback model no longer seems to be a very good way to explain this kind of variability. Yeah.
Was this tuned? So is this a typical example of out of tuning forecast going bad, or is this the Kane-Zieback model out of off the shelf?
This is the Kane-Zieback model plug and play with radiative forcing. Is that what you're asking? They didn't do any tuning to it. They simply just hit it with radiative forcing. Yeah. They did play with my coral data. Okay, they moved these means up and down in a kind of in a way that didn't shift them relative to each other, but matched the mean instantiation of their Niño 3. That's what they did. Mike Manning, Mark Kane. Okay, so this is the citation for this paper.
The blue cloud has been moved as a whole to give an optimal fit.
The blue cloud has been moved as a whole to give an optimal fit. Let me also say.
That with green as well. That would look fine.
Yeah, I've actually. Well, no, I use their. The way they move their blue cloud, I move my green cloud. So that this is all consistent.
What would be interesting would be what would be interesting if you use the free blue and the green, and then you do the moving exercise, whether you could get the same kind of.
Absolutely, and I wish I had the Niño 3 data. It just came out, so I hope to get that from Mark Kane and company to do that. That would be great. But the bottom line is, it's going to be hard to get this green data, which falls so much lower than these blue pieces. It's going to be hard to explain that with this model ensemble mean. I think that's fair to say. Now, the corals could be crazy, and we hope to reproduce them from other islands. But as of now, as an ensemble, they are kind of showing us cooler conditions. It's not just one of them. It's now 7 of them.
Could you comment on your certainty you have with the timing?
It's plus or minus 5 to 10 years. It's very, 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 very high resolution radioactive dating. Okay, so let's just move on. I wanted to show you the whole plot. This is not monkeyed with. This is my raw data as it comes off. So no Mike Mann touching it or anything. And it also shows the modern coral, which I think is really relevant to this discussion too. So what you can see is the medieval warm period, the earlier millennium. This is called medieval warm period, and I have all these cool corals here all of a sudden, so I've stopped saying that. So the medieval climate anomaly kind of corals with these cool guys here, moving to kind of a millennium average for these two realizations, and then post-1976, a sharp change towards warmer, wetter conditions in the tropical Pacific. That stands out very, very sharply. So this is the whole record that was these pieces back here. Some have not been published, but otherwise it's available. Okay, so the bottom line here, I think, is that this is very, very interesting time period in terms of, was this radiatively forced or not? What caused this anomaly in the tropical Pacific, El Nino? And then we're going to look at one other example of interesting thing that came of this, which is this one piece in the 12th century, which you can see the character of the record changing a lot. This is one single coral that grew during 70 years in the 12th century, and you see some decadal scale variability here, and then this is an arbitrary red line, and then a lot of El Nino variability after that. So you have the suggestion a kind of a threshold crossing or something happening suddenly in this coral, this one coral, from a decade to decade, which is all I wanted to say about this. So let's wrap it up. Okay, I think there are a couple of lessons relevant to ENSO in a greenhouse world that I hope I've convinced you of, or at least thrown some uncertainty or brought some highlights to the El Nino discussion. If the ocean thermostat theory is right, then mean state should be moving towards a La Nina-like response, all else being equal, which it's not. So, but that's one of the things to think about is if this is correct, that's what it means for the future. ENSO models and Palmyra corals, the best reconstruction we have of the corals in the last millennium, show that abrupt changes in ENSO properties are fundamental to the tropical Pacific ocean atmosphere system, whether forced or unforced. And I hope that I've convinced you of that if the corals are correct. We hope to get more of them. And thirdly, the tropical Pacific definitely played a role in abrupt climate changes of the past, whether as a trigger or as just a feedback response. And it should be considered in models or theories that try to explain how this global signature of abrupt climate changes happened. There are still more questions than answers. Does radiative forcing explain a significant amount of ENSO variance? ENSO is a noisy beast. So, are you actually going to see a statistical response to the radiative forcing? We're going to keep looking at the Paley record for that. And the question that Carl got at, and I think the question that George has been consumed with, how does mean state affect the response of the tropical Pacific to radiative forcing? So the Kane-Zibiak model, just plugging it in, radiative forcing with volcanic and solar events and looking at what happens, is probably not the best way to look at it. If you're much cooler in the early millennia, maybe your response is different, extratropics. There are a whole other suites of things that need to be thought about before you can answer that. So I'll stop there. Thanks. Any questions?
Could you go back to the one where you said you saw an abrupt change?
This guy, the next guy.
Yeah.
This guy.
Okay, so I guess without the red line there, I'm not sure I would have picked that as visually different. I mean, the excursions get a bit bigger.
Let me tell you, Carl, that this you can comment on personally because I used one of your techniques to look at for right or wrong, to look at whether I could reproduce this difference in ENSO variance from this epoch to that epoch, assuming these were epochs by doing your spectra at equal variance and random realizations by changing the phases and things. So, and I did that, and I found that 2% of those realizations would exhibit this kind of a change in ENSO variance, which is quite large if you do the math out. And then 98% of the time they couldn't. So that's the best, hopefully the best answer I can give you.
But what you do, of course, is, again, we have not addressed the problem of that this is not temperature, what you're showing. It's just showing something chemical.
Okay.
And so what you need to do actually is to apply an error model.
Right. Okay.
And then I was wondering what comes out at the bottom. I mean, if you process that time series, I have no doubt that this is all correct. But whether this has anything to do with temperature,
okay,
on which time scales, I have no idea.
Well, let me just say that I did not show you the calibration interval for this reconstruction, which it covers from 1886 to 2000. And basically what you see is that it's 0.65. The monthly data correlate from the coral to the instrumental. Nino 3.4 is 0.65 raw. That's pretty good. And if you filter for El Nino, the correlation for 2 to 7 year bandpass, the correlation goes up to 0.85. So we are seeing El Nino temperature here.
Which is normal if you reduce the number of degrees of freedom that the correlation goes up.
Of course.
Also, we know, I mean, since we're talking about what this means, we know, for instance, that in our own reconstructions based on proxies, they diverge after a while. I mean, then they're not, even though they're good, mapping on the same instrument, in the same instrumental data, if you go back, they contradict.
Sure.
And so we somehow must, if we think about proxy data, we have a tendency of saying, well, what the proxy data tell us, that's it. But we are not applying a proper error model of that. And then, of course, if we come to more sophisticated diagrams, like the one at the bottom, then this looks nice, but we cannot assess what is the effect of an assumed, and let's just assume it would be white or red noise with the timescale of El Nino, what the effect would be.
So I
Yeah,
always
I
think there's a
do
question
agree with
mark
that general statement. And as of yet, we don't have any other corals from any other islands across this period. There's an assumption about the El Nino impact in this area not changing with respect to temperature and rainfall impacts. So there are several assumptions and not a lot of data, and so we cannot basically deliver unless you want to chat with me afterwards. More of a reliable
Are there
area.
people on Palmyra during this period?
No, there weren't people on Palmyra until, well, one may argue, World War II, but there were some Polynesian canoes.
So
But
what I want to say is that what we collectively have to do is we have to think about these error models. And then we can just add, we can do Monte Carlo experiments, and we add then realizations of this error model, and then you get hundreds of these curves where all equivalent, you would say, because you assume that this error model is correct, and you would get 100 diagrams at the bottom.
well, that's what I was trying to say with Carl. That's what I actually did with Carl's, was it 97 paper, where you lay out.
Just presumably using red noise.
Right,
And
right.
asking.
Right.
And then it's
But did you superimpose an observation error? I think that's what you referred to with error model. So in this Monte Carlo analysis, you also have to superimpose
Right.
a calibration error,
Right.
which if you do that, your power goes down.
Yeah, you're right. I did not do that.
And that would be interesting.
That would be
Assume that
interesting.
yeah, but 0.85. No,
Thank you.
This is the end.
Okay,
This is
let's
the same.